Now, the other part of the periodic table we haven't talked about yet was the number with lots of sig figs usually, and that has different names, but right now let's call it the atomic weight, all right? Now, boron we saw in the last slide, there's a lot more boron 11 than there is boron 10, and the atomic weight is kind of the average of all of the different isotopes. And when you find an average in chemistry, you take essentially like the decimal amount of it around. So like there it says 20% boron 10. The decimal version would be 0.2 and the 80% would be 0.8. You take those numbers and you multiply them by the masses. And if you then add that together, that gives you the overall weight. This is statistics in a very zero level kind of discussion. So let's say we wanted to estimate the atomic weight, which is basically the average of all the isotopes. Boron has boron 10, and that's where that 10 comes from, and there's boron 11. And if you take the 20% and you divide by 100, you get 0.2, and if you take 80% divide by 100, you get 0.8. So in your calculator, 0.2 times 10 plus 0.8 times 11, it comes out to be 10.8. And that's how they find these atomic weights. And if you look on your periodic table right now for boron, it's going to be a number about 10.8 as well. There's a lot of periodic tables that are better than this calculation. You'll have more sig figs, but this is how they get those numbers. So it's the mass of the isotope times its decimal percentage plus the mass of the other isotope times its decimal percentage. You add those together to get the overall weight. So all of those numbers are experimentally derived, all right? They do change every once in a while. They'll go through this major changes to the periodic table because they have better values for mass. But now you know the secrets of how those numbers come out. Notice that 10.8 is not the 10 of boron 10 or the 11 of boron 11. That's an independent number, and that's going to be important to us. Lithium has two main isotopes. The lithium 6 is about 7.5, and the lithium 7 is about 92.5. Now, if you look on the periodic table, my particular one right here for lithium, the atomic weight 6.941, and yours might be a little different, better, worse, and stuff is fine, but this is how these numbers come around. So the atomic weight is 6.941, and notice that it's closer to the lithium 7 than 6, like 6.941. Here, let me write it in here. This is kind of cool. I can do this. Anyway, 6.941 in my periodic table is much closer to 7 than 6. Like if I rounded up 6.9, it would be 7. That's because most of lithium is lithium 7. If this would have been 90% lithium 6 and only 10% or so lithium 7, then the atomic weight would have been closer to 6, maybe like 6.1 or something like that. Silicon has several isotopes, and you can see though right away that silicon 28 is more than 90% abundant, which means more than 9 out of 10 times you're going to have a silicon 28. And if you look on the periodic table, you'll get a number something like this. My periodic table lists 28.09. Again, yours might be a little different. And again, because the most abundant isotope was silicon 28, it makes sense that the atomic weight, which is basically an average, will be closest to that as well. Here's a problem. You've got 3 different isotopes, all right, 72, 73, and 74, and it's some random element E, okay? And the question is, which of these is the most reasonable atomic weight? And you can see there's 72.1, 72.8, 73.4, 73.8, 74. Okay, so when I see a problem like this, I start off by looking for which isotope is most abundant. And you can see that the most abundant one is definitely 72. So the atomic weight is going to be closest to 72 because it's the most abundant, all right? However, it's not like 90% abundant. Like with the silicon, we saw like a 90% made the abundance close to it. This is only 50%. And we do have a pretty good amount of 74 and 73. So let's start here. I don't think it would be 74. All right, that's out because it's not 100% the 74 isotope. That doesn't seem reasonable. And because it's more than 50% 72, I would cut out those as well. I don't think that's very reasonable. However, it's not like 90% plus of the 72 isotope. I don't think it's going to be 72.1 either. If the isotope 72 was like 90%, then I could maybe see a 72.1, but it's just a little more than 50%. I'm going to argue that answer B is the most reasonable, all right? And that certainly is what it should be and stuff. So because isotope 72 was more abundant, it's going to be close to 72, but because it wasn't like 90% abundant, probably not 72.1, but somewhere not too far from there. Nitrogen has two main isotopes, nitrogen 14 with a mass of 14.0031, 99.629%, and nitrogen 15, 15.001 AMUs, 0.3701%. We're using a lot of sig figs here, and that's what people do when they calculate the numbers you see on the periodic table. So from these two, we can calculate the average atomic mass. And again, what we're going to do is we're going to use the decimal version of those percentages and multiply it times the isotope mass, and we'll add that to the same thing for the other isotope together, and that'll give the average mass. So what we have right here, 99.6299% divided by 100, 0.996299, and we multiply it by the mass of the isotope, 14.0031. Now the other one was 0.3701%. So that number divided by 100 is an even smaller number, but we'll multiply that by that isotope mass. And we'll add these two things together. If you do this, 14.0068 AMU. And if you look on your periodic table, that's not too bad. Now, my periodic table, which honestly is a little cheesy at this point, 14.01. So this is a much better sig fig value. 14.0068 has much more sig figs than 14.01. Mine's not bad or anything like that, but obviously you can do better. Gallium has two main isotopes, gallium-69 and gallium-71, and the average atomic mass, 69.723. We can use this information to calculate the percent abundance of each isotope. And this is kind of an interesting problem. Now, first of all, I want to talk about what's happening right here. And to talk about it, I want to use a number line. Now, a number line, it can be really helpful with these kind of problems. And on my number line, I'm going to have 69 and I'm going to have 71. And that's because those are the two isotope mass numbers that we're dealing with. But in addition, the halfway point would be 70, and you can see that the average of all these, which is what the atomic mass is, 69.723. Now, this average, which you can see on the number line, is a little bit closer to 69 than it is 71. And that's useful to us because that's going to tell us, if we've done this problem right, that the percent of 69 is going to be greater than the percent of 71. Now, it's not like super close to 69.7. I mean, it's not far away, but it's not super close either. So it's not going to be like 90% 69 and 10% 71, but we can use this kind of information to at least make the suggestion that the isotope of the 69 gallium will be a greater percentage than the isotope of the 71 gallium, or gallium-71. To solve this, it's not too bad. What we can do is set up our equation so far. And remember that you take the decimal version of the first isotope, which we don't know, I'll call it X, and you multiply it by the mass of that isotope. Then you add it to the decimal version of the other isotope, which we don't know either, let's call it Y, and you multiply it by its mass, that number, and that equals the average, which is the atomic mass. So you can see right now we have two unknowns and one equation. We don't know x or y. And really, to solve equations in math, you need to only have one unknown in an equation. So we need another relationship that somehow is going to break our two unknown variables. And because we have only two isotopes, the two percentages together have to equal 100%. So if you had 50% A and 50% B, that would be 100. Or if you had 90% A and 10% B, that would equal 100. And we only have, in these types of problems, two percentages. 1, which would be the decimal version of 100, equals x plus y. So y, we can substitute in then 1 minus x. And that's what we're going to do on this next slide. We're going to put 1 minus x in there for y. Then we have only one unknown, x, all right? We can solve for it. We can get all the x's on one side, all the numbers on the other side, solve for x. Then we'll come back to this equation I circled. 1 minus that number, 1 minus x will equal y. And remember, x and y have to be positive numbers less than 1. So here's the x and the y, and here I substituted in the 1 minus x for it. So what we want to do here is we want to solve for x. Now, I skipped some steps here, and I'm going to let you try this problem on your own. But if you want me to get you a little bit farther, you can say here that 69.723 equals 68.9257x. That's basically these two right here. Plus, you're going to use distributive property, which means 1 times the 70 number, 70.9249. And then I'm going to go minus x times that, minus 70.9249x. So now my handwriting is sloppy, but you have two x's. First x minus the second x will give you just so many x's. Then you can subtract the 70 number from 69.23. You'll have x's on one side, numbers on the other side. If you did that right, x 0.6012, which again times 100%, 60.12%. And if you go back to the other equation, 1 minus x would be 0.3988 or 39.88%. Now, this is a good time to step back and see if this all makes sense. Earlier, we said how the abundance of the 69 isotope must be larger than the 71. The average, 69.7, is closer to 69 than it is 71. And you can see that's what we got. We saw that it's about 60% 69 gallium 69, and it's about 40% gallium 71. So all this is fitting in place. This is a cool way to check yourself on these calculations if you're ever uncertain. Try this on your own. And of course, if you get stuck, this is a good thing to email me, take a screenshot of what you're doing or a picture on your phone, whatever, and say, oh, I need help, I'm stuck. And that's when I can help maybe you to figure out how this all works out. It's a cool technique. It only works when you don't know the abundance of 2 isotopes. It doesn't work if you have 3, etc. Antimony, SB, number 51, has 2 isotopes. First isotope, about 121 at 57.20%. Second one, almost 123 at 42.80%. Average atomic mass, 121.7. And this question is important. Will you ever have one atom of antimony with 121.760 AMUs? And the answer is a resounding no. You are not, if you have a big bag of antimony, you start pulling out antimony atoms and you can somehow magically figure out their masses automatically, you'll never have a mass of 121.7. 57.20% of the time, you're going to get an antimony with 120.9038. And 42.80% of the time, you're going to get an antimony with 122.904. Remember, the 57.20 is almost 60%, which is like 6 out of 10. 42.8 128 is about 40%, about 4 out of 10. So 6 out of 10 times the 120.9 and 4 out of 10 times roughly 122.9. But you're never going to have 121.76. The 121.76, the numbers you see on the periodic table, are statistically generated numbers. And in the United States, sometimes they'll say that the average family has 2.5 kids, all right? But if you've ever gone to like anybody's house in the United States and you go up and you knock on the door, you won't see 2 regular kids come out and some kind of like half kid come out, which is just gruesome and morbid. And I apologize for the bad imagery, but you don't see that. You'll see houses with 2 kids and houses with 3 kids and houses with 1 kid and houses with 4 kids and houses with 0 kids and houses with 5 kids, but you won't see like a half kid, all right? That's just repulsive. Anyway, statistically generated numbers are artificial, all right? Like you won't have a family with 2.5 kids, you'll have families with 2 and 3. And 121.760 is the same as the 2.5 kids. It's an artificial number. You'll never have one atom with that mass, all right? There is a use for that mass, and it's a super cool use, as we're going to see. But for right now, I want to be very clear, you're never going to have one atom with that exact mass.